So yesterday we looked over a linked list, um, saw how a linked list worked up under the hood, and then you went and worked on the implementation of the queue. Going back over a linked list a little bit, what operations can be done efficiently with a linked list? With a linked list, what operations can be done efficiently? We will define efficient as O to the one time, and anything else is not considered efficient. So what can be done with efficiently with a linked list? Anybody? Remember, one thing with a linked list is that it doesn't have indexes. And when we have indexes, we've got to shift everything over. But with a linked list, if we were going to append or prepend, add to the head, add to the tail, remove from the head, remove from the tail, efficient operations are owed to the one time because they involve a few quick change of data pointers. And kind of accordingly, what operations are not so efficient with a linked list? Yeah, reading it, whether you want to print it, like we'll do a method today that involves that with the doubly linked list because you're going to have to iterate over everything. Um, Also, another thing that you can't do with a singly linked list is join two singly linked lists in one time because of the fact it does not have a reference to the previous. You are not able to join the tail of one to the head of the other. You actually have to iterate through both sides. So that said, you're working in end time at that. We'll talk a little bit more about these runtimes here in a second. Last question I've got, and I want somebody to answer this. In a linked list with only one element, self.head will be equal to what? A list with one element, self.head equals to a primitive value. What is that? Somebody type or talk.
Wouldn't it equal that element?
Can you repeat? I had to turn my volume up. You were a little low.
I said, wouldn't it equal that element that you're referring to?
Yes, with one element, it equals that element. And that said, what is the self.tail equal to if we only have one element?
It's also equal to the head, and then it's pointing to none.
Correct. The value of the head and the value of the tail both will be the same value. The head will point to the tail will point to none. Very nice, complete description of that. Did anybody, we're not going to get into any details here because we don't have time, but did anyone have any not do? Make this anonymous, send it to the channel. If you have any questions, anything you might have from the cues, yesterday's lecture, doubly linked lists. Looks like 4 no's. Anybody else that's going to vote? Vote now, type a question in if you have one. Otherwise, we're going to keep moving. And if you don't have these down 100%, that's fine. We're going to be working with these data structures, but I wanted to make sure and close any gaps and give everyone a chance to talk that would be looking for an answer for any question. I'm going to go ahead and share my screen. So today we're going to implement a text buffer data structure that is backed by a doubly linked list. Some of you may have already completed the doubly linked list. Some of you may have read ahead and been, oh, hey, I know how to implement this, and that's cool because that will be part of what you're doing today. For now, I've got a file in here that is the doubly linked list that we will just be importing in the code later on. And then I just have initiated the code that we'll walk through that first little bit, and I've got the tests ready, but that will come here in a bit. For now, we were going to have a little bit more of a talk about the doubly linked list and the text buffer. So this text buffer will be backed by a doubly linked list. That means we'll be creating a text buffer with the doubly linked list as the underlying data structure. It's just another way to word it. Can anybody tell me what a text buffer is in general terms? Anybody tell me what a text buffer is? Text buffer, what's a buffer in general in computer science? It's a temporary place to do something. Anybody? Think of a text buffer simply as a temporary space to store text. Think of a text editor in a very simplest form is utilizing a text buffer. So this is something I want to answer, and I'm going to wait until people start answering. What sort of operations do we usually perform when we're working with a text editor? Think about Poly's problem solving, and we're told, okay, we need to implement a text buffer backed by a doubly linked list, which we'll talk about in a second. And we need to implement a text buffer. So we're going to have some methods on that text buffer to be able to use it. And think of a text buffer like we're working with a text editor. Your text editor like I just had up, VS Code. What are some operations that we usually perform when we're working with a text editor? Insert, yeah. What else? Come on, a couple people type. This isn't even really computer science. Write, delete, yep. Think about something like in a cut paste operation with a clipboard. What is something we may do with a text buffer? Something we may have to do that involves 2 text buffers. Something we were just talking about that a singly linked list doesn't do so well, but a doubly linked list might be able to handle better. Think about it kind of in terms of insert. If you're going to cut and paste and you're going to insert it in the middle of something, what are we going to have to do in this case on both ends if we're inserting it? Esteban typing. Copy over the text to a new buffer. Yeah, we might have to do that. Might have to join, is what I was thinking about, joining multiple buffers, joining the ends. And so, because some people might not have gone over it, or even if you have, it's worth talking about for just a second. So I've got a graphic pulled up. And I brushed on it yesterday, but a singly linked list, remember, one of the advantages of a singly linked list is you only had a reference to the next. There was no null here. You only had a null pointer at the tail at the end of the singly linked list. So on a normally singly linked list with multiple nodes, data points on it, it just has a next pointer, and then that final next pointer points to null. On a doubly linked list, it pretty much is what the name says for it. You have a next pointer and you have a previous pointer. So at the head, the beginning of the linked list, the previous pointer points to null. Obviously, these make sense. Next points to next, and the previous points to previous. Remember, I pointed out the other day, one of the problems is once you move along this linked list, this has no idea at the memory pointer, the space in memory that it came from A, and has no way of accessing it. So it's both a limitation and sometimes used as intentionally used as an advantageous feature. If you've ever done any studying on blockchain and cryptocurrency, they use technology very similar as a way of one of the rudimentary ways of protecting data. With the doubly linked list, we do have a reference back to the previous, and then finally the next at the tail points to null. Same rule, if you have an empty doubly linked list, you have a head and a tail that point to none, the underlying data structure. If you have one element, the head and the tail both point to that element, and the previous and the next point to null for that element. So today we're going to implement the text buffer data structure, and we're going to implement a few methods, and I'll just type them in here just for a little bit of reference. We're going to put in this string method. We're going to put in an append, a prepend, a delete front, a delete back, and a join. So a string, which is basically going to let us stringify this object in some way that we want to output it and output a string. An append and a prepend, adding to the tail, adding to the head with the prepend. Delete front, delete back, the same as being a pop off the front for delete front, and the delete back being the same as the name is slipped my memory in Python, and what is it, an unshift in JavaScript. And then a join, where you're able to join two of these text buffers. So I'll go ahead and put that in the channel. So like I said, the string allows us to call print on our text buffer to print out all of its contents. The append adds a character to the back of the text buffer. The prepend adds a character to the front of the text buffer. Delete front removes a character from the front. Delete back removes a character from the back. And join concatenates another text buffer onto the end of this buffer. These methods should be as efficient as possible. We can get most of them down to O to the 1. I'll just kind of throw it out there that one of these, 1, will be an O to the N. And a little later, we'll look at another alternative data structure and speak of it real briefly that also gets real close to this. But know that as in terms of a lot of things compared to an array or a singly linked list, it is more efficient. And something we're also going to talk about right now in another graphic I'm going to bring up, since we're on the subject of that, I might as well touch on it, is this is a simple graphic right here. Screenshot it if you want. I guess I can drop it in the channel, but you got something similar on that big O cheat sheet, but it's jumbled in with a lot of other things. But common methods that we would be calling with, that we just went over, that we would be calling with a doubly linked list, we show using both a Python list, which we've already gone over, how an array functions, and how the append adding to the end is only O of 1 because nothing has to shift. The prepend is in time because it has to shift every element over 1, so it depends on the length of the element n. Delete front is also O to the n because you have to shift every element backwards 1 after you delete the front. Delete back is the same as a pop. It's O to the 1 because you're simply pulling off the final 1. Join, remember I said you have to iterate over everything because you don't have a reference, a way of, you basically got to create a new array by iterating over the 2 old arrays as you do it under the hood. And string, of course, like we were talking about earlier, if you're going to print something, you get O to the n time. With a doubly linked list, you can append, prepend, delete from the front, and delete from the back, and join all in O1 time, simply because you have a forward and a backwards reference. So in this case, all you have to do is simply take your memory pointers, rearrange some memory pointers like we'll work on later, and you get all these O to the 1 times. It's still, for the string method, is O to the n because it's got to iterate over each individual node to know what is there to be able to output as a string. Real quick, we'll brush over the double-ended queue. I'm not sure why they put this in here, but all that you need to know about this at this time, remember a queue is first in, first out, just like a line at the bank, a line at the grocery store. And a double-ended queue, remember that the tail of the queue is going to pop and the head of the queue is going to be adding, well, I guess I'm using the wrong terminology. You're going to dequeue at the tail and you're going to onqueue at the head, the beginning. So who goes in first comes out first. A double-ended queue allows you to perform both operations at both ends of the queue. So if you could think about it, you can onqueue and dequeue off both sides. This allows you to append, prepend, delete to the front, and delete to the back all at one time because you can perform both of those operations. Think of append and prepend, delete front and delete back, just like onqueue and dequeue, depending on which end it's functioning on, the head or the tail. So those are all allowed in one time. The join is still in time because you will have to, why would join still be O to the n time on a double-ended queue? You can push and pop at both ends, but why would join still be in time? Somebody answer. Remember, on a doubly linked list, it was not in time. It's one time because of the property that doubly linked lists have. What's something maybe that double-ended queue doesn't have? Why can a double-ended queue not join at one time like a doubly linked list? Sound a lot the same. Double, double. Somebody type. Somebody guess something. Anybody out there? Everybody hear me okay? Somebody type if you can hear me okay. All right, so while y'all are typing, why would maybe a double-ended queue, we talked about a queue yesterday, we can remove and add to each end of it, so that lets us do things in one time like the doubly linked list, because nothing has to shift. What's the problem with joining? Kind of like a string. When you join it, it doesn't matter that you can push and pop off of the end in the terms of being able to do it in one time. With a doubly linked list, like we said, and like we'll demonstrate, you're simply rearranging a few memory pointers, but with a double-ended queue, you've still got to iterate over the entire structure of both structures to be able to join it. And with a string, the same, to be able to print it. So to get all the methods as efficient as possible today, we'll use a doubly linked list. And like we've talked about, the advantages that we have, excuse me, we get the most optimal runtime with this because everything besides actually print it is in time. And to be sure I was clear on the last one, something I just realized that I might have said wrong. On the queue, if you're having to join one queue to the other, you can actually just join. You're constantly removing from one and adding to the end of the other, hence why it's in time. You're not actually having to iterate over both of that double-ended queues, but if you wanted to join two double-ended queues, you'd have to iterate over one depending on where you're joining to and add it to the other. Actually, you could do it both ways since you've got both access to both operations on both ends. But nevertheless, as it goes up, you're going to have a linear relation to the data because the more data you add, the more data you're having to join to the other queue. So to implement this text buffer, remember that we are going to be using Python. We have this doubly linked list that I talked about that is the underlying structure. You may or may not have used it. I'm going to type here in the channel a few things. I'm going to tell you what the available methods are on this doubly. So an insert after, an insert before, or excuse me, I'm using the wrong terminology. So we would call it add to head. We will have remove, of course, from head, add to tail, and of course, remove from the tail. And the actual implementation of these is not important. Just remember that you have access to these methods. And then we'll have move to front, which allows you to take any element and move it to the front of the list. And then we'll also have move to end, meaning moving it to the tail, moving it to the front, meaning moving it to the head at the beginning. And then we will have a delete method as well. And we will have a get max method that just gets you the maximum value on that. So these are the methods that are going to be available to you. You can reference back to them. So I'll drop this base code in the channel if anybody wants to code along. And of course, I'll post the regular code at the end. But here's the base code for what we're doing today. The test in the main. And like I said, we import doubly linked list from the doubly linked list, and we implement a class of a text buffer. So we are going to init and then take in the self that we always do, and we will say init equals none. As we talked about yesterday, that equals none simply sets a default to it. The init allows us to bring in an initial string to that doubly linked list. So we say self.contents equals doubly linked lists. If init is not none, if we actually put something into init, a string in init, we're just simply going to say for char and init, iterating over the entire string, self.contents.add to tail, adding to the end the character, and we will build that singly linked list. Remember, add to tail was one of the methods that we have available to us in this phantom doubly linked list. I said singly linked list, but we're adding to the tail of the doubly linked list if we have an init. If we don't have an init, we start out with an empty text buffer, an empty doubly linked list, the same as having head and a tail pointer that point to null and nothing else. Same rules that we've been talking about. Down here, we'll talk about this a little bit more later, but in the main, we are basically just instantiating a text buffer with an init of super, joining it to the string califragilisticexpialidocious, and we're printing the text each time. Then we're appending is at the end with spaces around it, and then we're joining it to another text buffer, weird. So we're trying to get supercalifragilisticexpialidocious is weird. And then we're going to delete the back 6. We're going to prepend hey, and then we're going to delete the front 4. So we'll see that in action at the end of this. So our job right now, the first thing we're going to do, and I'll go over briefly while we're doing this, people ask what the str is for. Does anybody know off the top of their head what the str allows us to do? I've kind of brushed on it, but yeah, it allows us to change the object to a string. And we'll see later on, if you don't use the str and it actually, what it, I'm trying to remember what it defaults to, like an RPR that is just representing the object. And you get, well, I'll try to show you later on in this, we'll change a little bit of the code around, but you basically get a bunch of nonsense, but this allows you to represent it as a string. So all we're going to do for this, if we want to output a string, what would be maybe the first thing we would do? I want a hint, it's declaring a variable. We need to initialize that variable to a value. What would we maybe do there? What would we maybe want to do? Yeah, have a blank empty string. That's all we got to do. And then we will say current. Remember how we went the other day when we iterated to a singly linked list, say current equals self.contents.head. And the same as we did with the while loop yesterday, while current. And we will just say s plus or equals current dot value, remembering that, of course, that node has a value. And then what would be the last thing we had to do after, if we're iterating over current in a while loop? Iterating over current in a while loop, we are building up our string one character at a time as we iterate over that input string for init that we overrode the default of none. We say while current s plus equals current dot value. What's the last thing we would need to do? Well, we'll have to return s at the end. What's the last thing we need to do within the while loop right here on line 15? What's the last thing we'll have to do? Remember, current is serving as the iterator in a sense. We're just say current equals current dot next. It will have available on that node. Remember the methods that we also, you can reference back the nodes that we implemented for the singly linked list. Just know that in a doubly linked list, we're going to have the value, the next, and the previous. Instead of just a value and a next, there's a value, a next, and a previous. So of course we have helper methods, getters that allow us to access those values like we were doing yesterday. And then we'll just return s once we kick out of that while loop when we are done with that. All right, so next we talked about all of the methods that we were going to implement. We've got the init, we've got a string. So the next thing we're going to do is define an append. What should this append take in? It's going to take in self, of course, but what argument is it going to take in? We're going to append something. What argument does it need to take in? Append, add to the end, add to the tail. Yep, the string to append, exactly. So we will just call that string to add. And we will just say for char in string, once again, iterating over the string to add self.contents.add to tail. Remember, we had access to add to tail printed over here. And so we will simply add to tail. What are we going to put in there to add to the tail? Tell me what to type in there exactly. Somebody. Everybody should know this, just looking at this intuitively.
Char.
Yes. You said char? Yeah, char. I'm just going to add the char. And that's all we have. We don't have to return anything. We're just simply adding to the tail. Char. So the next thing we're going to do is have a prepend. What are we going to have to take in for a prepend? Prepend, add to the head, add to the beginning. What argument do we have to take in if we're going to prepend a string? Quicker somebody talks, quicker we can move on. If we're going to prepend, what are we going to add?
String.
Yeah, string to add. Same. All right, if we're going to prepend, we're going to do the same thing, but we need to think about this. If we're going to prepend a string, so we're getting a string, and we've got to add this string to the beginning in the same order that we've received it. What's a little bit different here? When we appended, we just iterated over the string and just kept adding each character. But if we're going to prepend in the same order, what's the problem?
Insert.
You need to what?
Insert to the first index.
Well, yeah, you're going to be...
If we are thinking about like it's an array we just append for the, if we want to add the first one, every time we need to iterate and add them to the first.
Well, what I was more trying to get at is when we're appending, say we get the string ABCD, we just start iterating, starting at the head like we did when we set the current as self.head. Or excuse me, we just start at the head, we're starting it for char and string to add, and appending, excuse me, we're adding to the tail. So if it's A, B, C, D, we're simply, okay, at A, add to the tail A. At B, add to the tail B. C, add to the tail C. D, add to the tail D. If we're trying to append A, B, C, D, and then our current string, what method are we going to use that we've already shown over here if we're going to add to the head? What method might we use? If we're going to prepend, which of these methods are we going to have to use? These methods that allow us one node at a time to manipulate the linked list. Maybe have to use add to head since we're going to add to the head. The problem I'm getting at here is that with a prepend, we can do the same thing and say for char in string to add, But the problem is we've got to iterate over this differently. So what we can do is use this Pythonic notation. And this basically says start at -1 and iterate all the way back. This is iterating over the array in reverse. It's the same as having a counter at length -1 and decrementing it down to 0. This is the Python notation for iterating over. Because you understand if you have A, B, C, D, you've got to append D first, and then C, and then B, and then A for it to go in the correct order. Otherwise, it would flip your word around in the text editor. So we're going to say self dot contents the same dot add to head char. Any questions? Any questions over any of these methods or the reason that we're implementing them the way that we are? Any questions about how the append, the prepend, the string, the init, text buffer in general, why we're using a linked list, the runtimes that I showed you? Any questions? People vote. There's 6 people in here. 2 people have voted. 3 people have voted. Any questions? Ask now if you got anything. We've got plenty of time. All right, 5 no's. All right, so the next method we were going to do was delete front. And remember, this is going to be removing from the head, the beginning, the front. So if we're going to delete from the front, be the same, but we're going to have characters to remove. And I kind of just spelled this one out because we could have a couple different options here, but this is simply an integer that's saying how many characters to remove from the front, how many to remove from the front. So if we looked at these methods over here, if we need to remove from the front, which of these methods from this doubly linked list we've been given access to and these methods we've been given access to would we want to use for delete from front? Which of these methods that I have highlighted over on the Slack on the right would we use to delete from the front if we give a specific number of characters we want deleted from the front of the doubly linked list? Saw somebody typing. Yeah, remove from head. So do a for loop here, and we will say for underscore in range of chars to remove. And so remember, all we're doing here, who can tell me why there's this underscore? We normally do for char and string to add, for char and string. Why just an underscore?
We don't want to create the charts. We just want to iterate the range of like length of the chars.
Yeah, you don't, well, not just the char, but anything. That's just indicating that you're not going to use that placeholder. So, like right here, when we say for char and string to add, and if we just said add to head A each time and you bounce down off of this, normally it's not doing it. I think this should throw an exception when you have an unused placeholder. At least the linter will catch it because it's not good practice. But in here, yeah, we're not actually using this. We're just using this to iterate the number of times. Remember, in range, so it'll iterate. If we say remove 7 characters, it will iterate over 7 times, and 7 times it'll tell the contents remove from head. And then likewise, if we were going to delete back, what method would we maybe use that's over there that I had highlighted, still have highlighted in gray? We've been told how many characters to remove. Do the same thing here for underscore in range. What method will we use? What method are we going to use to delete from the back? If we're going to delete from the back, what method over here would we use? Yep, remove from tail. Self.contents.remove from tail. And I'm going to give everybody a 5-minute break. So come back on the hours, so at 10 o'clock your time, and we will go over the join and a couple things we run into. And then we will go ahead and test this out and move along from there. So everybody take a break. I'm going to pause everything. Be back in 5 minutes. All right, give everybody just a second to come back. We're reaching the hour right now. All right, everybody should be back. So I just want to ask one more time, if anyone has any questions, you don't need to vote or anything. Just go to the section right here. If you have any questions, that now that this is all maybe set in, you've thought about it. Remember, we've got a doubly linked list with these methods available to us. Add to head, remove from head, add to tail, remove from tail. Because remember, we have a next and a previous pointer. This is easy to do in one time. We also have move to front, move to end, which allows you to move a given element to the head or to the tail. A delete, which allows you to delete an element. I keep calling it an element, more properly a node. And a get max gives you the maximum value of the nodes in the linked list, pairing the Unicode of a string, comparing integers, floats, or whatnot. And then we've talked about the methods that we've done after we made the text buffer. We just initiate a doubly linked list. If there is an init, an initial string that goes in there, we iterate over it and add to the tail. Then we have a method to be able to print the string, simply starting with the head, and while there is something in that string, it adds it and then returns it so that we get to see a printed value of that object. And append, a prepend, delete front, delete back, pretty self-explanatory. So now we've got the join that we talked about that we can do with a doubly linked list in one time. And why are we able to do a join in one time with a doubly linked list? Somebody type, why can we join in one time with a doubly linked list? What does a doubly linked list have built into it that allows us to do that? What does a doubly linked list have that allows us to join in one time?
Join to object. I don't know.
Join to why can we take one text buffer, this class that with this object, this class that we've instantiated, one text buffer of this string that we're storing in the buffer, why can we join it to another buffer in one time? Remember, if it's an array, remember we've got to iterate over each one, or if it's a singly linked list, we've got to iterate over the one that's being added and continually add it piece by piece to the initial that we're adding to. Why with a doubly linked list do we not have to iterate?
Because we know the head and tail.
Yeah, and what do we have for? We have a head and a tail for the both of them, but what do we have access to on that head and tail with a doubly linked list that allows us to not have to iterate?
You know each of the objects, previous and next object.
Exactly. You have a previous and a next pointer. So when you have a previous and a next pointer on both ends, you're able to join those together it's actually in a few operations, but it will go down to O to the one time because it's going to be a handful of operations. You'll have an integer value, and of course that reduces to O to the one with no greater values involved in it, involving n squared, anything like that. So for here for the join, we're going to take in self and we're going to take in other buffer. What might be the first thing that we did once we started this? Something we're not going to do, but something we might do just as a safety check, just as good programming practices. We didn't do anything similar with the other ones, but it's going to be real important here because to be able to join these, we're going to have to access methods. What would be a good idea to check at this point? What's a good thing we might want to look for? Just think about programming. We need to join two buffers. These buffers are going to be instances of the text buffer. Text buffer is an instance with an underlying doubly linked list. We're going to need access to those doubly linked list methods that we talked about over here. Anybody? Might want to check to see that the other buffer is indeed a text buffer and that someone just didn't feed us a string. Be a text buffer, you need to have an instantiation of that class and then put the string into the init for that class. So for this right now, but we'll add something at the end, we will just say self.contents.tail.next. The tail, the end of self, if I can spell it right. Self.contents.tail.next equals other buffer. And what are we gonna set it to? Other buffer.
Head.
Yeah, contents.head. Then if we did that, makes sense that we'll say other buffer contents.head.previous. So we've just joined the head and the tail of the first with the head of the buffer that we're adding, the beginning of it. We're going to say other buffer, the one we're adding .contents.head.previous. And what are we going to point to for that? The previous of the new head is going to be the what? It's going to be part of the old. It's going to be part of the old, so self.contents. The head's previous is going to be the old's
Tail.
Yeah. There you go. And then we will say other buffer dot contents dot head equals, what do we maybe put here? We'll set it to self.contents.head, and then self, because it has a new head, because we've joined two, so we've taken away a head and a tail. Self.contents.tail then equals other buffer.contents.tail. Think about it. You've got two text buffers coming together. The tail of the first one becomes the tail of the second one, or the tail of the entire content, since we're joining it and it's going to be part of self. The tail becomes the old tail, or the new tail, and the head for the other buffer becomes the self.contents.head. Does that make sense to everybody? If anybody has a question, ask it now. All we're doing is rearranging memory pointers here. So we point the tail of the original to the head of the new. We point the previous head of the new to the tail of the original, self.contents. And then because there's a head for other buffer.contents, we put put that to self.contents because that head disappears. And the same for the tail and self.tail because it's been joined and now it's just a middle node. We set it to other buffer.contents.tail. And then, like we talked about, we'll add another method just for fun here. We can say join string in case somebody fed this up here. The check we talked about is string instead of a buffer. If we had initiated a check, an instance of type check, we can say join string, and we will say self string to join new buffer equals, what would we do here? We need a new buffer. Just like we brought a new buffer in here, we're going to make a new buffer. What do we need to do? If we just got a string to join, what will we need to do here for a new buffer? Remember, we caught that someone gave us a string and not another buffer to join, so we're fixing that problem. If we needed a new buffer, what would we want to do? Think about object-oriented programming. Think about classes.
Initialize new buffer.
Yeah, thank you. Make a new text buffer, and we'll just give it string to join because that's going to be the init. Remember that we have defaulted to none, but we'll give it a string to join. And then we will just say self.join, calling the old method. Now that we have a buffer, we will call self.join new buffer. And of course, there we go. And we'll just call this method with this buffer that's actually serving as a buffer. And if we had had a check here, it would catch it. I'm going to post one more poll and ask if any questions real quick while I look back over this code, and then we will try to run it real quick. Any questions over anything we've gone over up to this point, especially these methods since the last time I've asked, but any questions really covering the last 2 days, or any terminology, any underlying principles of these data structures? And I'm going to be looking at this code if anyone else is looking at it and sees anything.
Jonathan, can you go to the line 5 and I don't know what's that double linked list? We never initialize, just say double linked list.
So remember that for this, because some people have not finished building this out as part of the independent project this week, because it's MVP for today, we have a doubly linked list implementation in the background. We implemented something similar to what we did yesterday, but it's got a previous pointer and all the new methods associated with it. So these are all the methods. It's this file right here that I clicked over to. You got all these methods right here that are available over here. So from doubly linked list, we're simply importing doubly linked list into the self.contents is doubly linked list, and the dumb thing I didn't do was put that. Does that make more sense now?
Yes.
Yeah, sorry about that. And these are the kind of things I say, if you see them, call them out. This is a combination of me glancing at the skeleton code that we have, coding on my own, and trying to talk my way through it and pay attention to the board at once. I'm pretty good at multitasking, but I'm still getting this presentation / teaching thing down. So where I tend to falter is in the code, I'll miss little things, and then in my words, I'll miss little things. And so we're going to go ahead and run this pretty quick if no one's got any questions. Everybody answer the poll, yes, no, do you have any questions? I'm going to keep looking at this and anyone else that wants to look at it to see if we caught anything. And so we've got our test down here that we've talked about. It looks like we have no questions. So in this case, I'm going to go ahead and save this. Pull this up in the command line, and we will go to desktop, and we called this text buffer.py. So I will just clear this and say Python 3 text buffer.py and see what we get. And we get super. Remember, we initialized a text buffer and we didn't leave the init to be empty, none. We gave it an initial string, so we dealt with that right here, where the contents adding to the tail of this doubly linked list each character. So we get super. And the next thing we ask it to do is join the string califragilisticexpialidocious, and it joins it right to the supercalifragilisticexpialidocious. And then we append is, but we have a blank space on each side, so we get the is. And then we join to a new text buffer, and we put the spring in here, the weird in here. So this is a way of just instantiating that new buffer, and since we didn't do a check, we just can't put a string in where it defaults to this join string method up here in the check if that's necessary. So we get space is space weird, just like we see right here. We print that out. Then we delete from the back 6. Remember, the back is right here, so we're going to delete 1, 2, 3, 4, 5, 6. So we have is and a space here. And then we prepend, add to the head, add to the beginning, hey. Remember, we talked about the prepend having to iterate from the end of the string that we're adding. We had hey, an exclamation mark, and a blank space. So we see that. Then we see delete from front 4. So we delete 1, 2, 3, 4. We still have a space. So now we have a space, supercalifragilistic is, and a print, and it passes all the tests. Anybody have any questions over that? You can add them to this latest poll. Give everyone just a second to look at that, to think. No questions over anything that we have done so far. So your next steps for today, complete your implementation of the doubly linked list class in Python. I will drop all this text, this code, into the channel. We've seen that it works. What I will not drop into the channel is the doubly linked list. Now remember, on your implementation of doubly linked list, if you want to go back through and make this text buffer work with it, you need to make sure that your file is named doubly linked list, or you need to change the file name here and or the doubly linked list, depending on what you name it in your doubly linked list. But remember, this import will have to change. So you're going to complete your implementation of the doubly linked list. That's MVP for today in Python. And if there's time, explore some of the other data structures under the stretch goal, the LRU cache, which you should have available in your repo. I'm just pulling that up right now. So you say you've got the LRU cache here that you can work on. And of course, in the README, there's instructions on it right here. Or you could explore variations of linked lists like a circular linked list. A circular linked list is kind of neat because it has the ability to have a buffer that overwrites itself. So if you had a buffer and you only wanted it to store the last 2,000 characters or last 200 characters or last 20 characters, whatever your input was, it basically is a linked list, and it just runs where there is always a pointer. So what you end up having is the head and the tail. The tail points to the head, and the head vice versa points back to the tail. So you have a complete structure. It doesn't have a beginning and an end, truly. It just spins around in a circle. When it gets to the end, it starts out empty, depending on how many spaces you allot for it. And once it's full, it just starts overriding the head to the next, the next, the next, the next. So that's another thing that you can look over. Your repo is the same as yesterday and will be the same all week. Like I said, the sprint will be regular this week. I hope everybody took the time to look over and do their whiteboarding if you did have whiteboarding assigned today, which you should have even if you're not in my group. My group, you'll be presenting those the same on Thursday as you did. Don't forget to follow the workflow. If you haven't added your PM, if you're in another group, I know all my people did, do that. Don't forget to commit often, push up often. That's how everybody can see what you're doing. If you're not pushing up, everyone just assumes you're not doing anything. I've got in the channel, in the pins, I've got the videos for the entire week. So tomorrow, we'll look at binary search tree, which we will cover tomorrow, and the heap, which is a real pain that we will cover on Thursday. Anyone had anything else? Jump on your mic and ask it now. Otherwise, I will let everyone go and let you get back to work on your project. Anybody? All right, if no one has anything, I am going to go ahead and let everybody go. Thank you for this afternoon. If you have any questions, message me. Remember, there's PM coverage all through lunch. Message your PM. Use the help channels. So 20-minute rule, use the help channel, message your PM, message me. Good luck. And I'm going to go ahead and end this meeting and let everyone get on with your day and get busy. And I've dropped the code. I will post this video, and there's nothing else that I think I do need to post. If you're missing anything, put something in the channel or DM me. Thank you.
Thank you.
Thank you.